This is extending the ARMA model to seasonality and integration and trend, chapter 6 of analysis of time series. So in this chapter, we're going to look at various ways to add useful features to the ARMA model. And given the procedures that we've developed in the earlier chapters, we can go through some extensions to the model quite quickly. And it turns out they get statistically very similar problems arise. So we can use our existing understanding of ARMA models to extend to these other situations. So we're going to look at seasonality and differencing in this part and trend estimation in the next part. So the seasonal autoregressive moving average gets called SARMA, and it has the following general definition given in S1. So we have a polynomial in the backshift operator and another polynomial in the backshift operator to the power 12 applied to the y's, and a similar pair of moving average polynomials applied to the epsilon. I'm just using 12 as a concrete value here because most commonly when we have seasonal data, we have monthly data, but it could be quarterly, it could be anything you like. And the epsilon is, n is a white noise process, mu is the expected value of yn, and I've written out the monthly and seasonal polynomials here just to set the notation. So we use capital letters for the annual or seasonal part, and small Greek letters for the monthly part. So it's fairly clear this is a special case of ARMA because these, in particular, big phi of b to the 12 can be written as just a polynomial in B. So it certainly is a special case of ARMA. It has a particular factorization, but everything we learned about ARMA models, including assessing causality, invertibility, reducibility, these things are also going to apply to SARMA. Now, the length, the number of time points in the seasonal part of the model is called the period of the SARMA. It's 12 for monthly data, 4 for quarterly. Generally, this is not a parameter you're going to estimate. It's going to be something that's given by the structure of the data. So you could use PQ cross big P big Q52 for weekly data. Generally, ARMA methods don't work for data that high frequency, but you can try if you have such data and see if that is the case for you. But the thing you shouldn't do generally is look at your data, maybe look at the ACF, see it has a peak at some fairly arbitrary lag, like say 9, and then fit a SARMA model with seasonal period 9. It should be driven by the science of whatever you're studying. Here's an example to help you see the consequences of this particular specification of the SARMA model. Here are two models, S2 and S3. You'll see that S2 has yn depending on yn minus 1, yn minus 12, and epsilon n. So that sort of seems like it has a monthly and an annual part. S3 has an extra term of minus a quarter yn minus 13. And so here's the question, which of these is a SARMA model, either one or both? And so if we look at S3, we can write out the polynomial and notice a factorization. So let's the polynomial here, the ARMA polynomial in S3 is 1 minus a half x minus a quarter x to the 12 plus 1/8 x to the 13. And we can notice that that is 1 minus, if I take a factor of 1 minus a half x out, I get 1 minus a quarter x to the 12. And then the extra product term that comes out at the end of that is plus 1/8 x to the 13. So we're good. And I'll call this star. And I'll say, from star, we can rewrite S3 in the following way: 1 minus 0.5b, 1 minus 0.25 b to the 12, yn is equal to epsilon n. And this, we put it in the form of a SARMA. S3 is a SARMA model. Now, if you think about it, any SARMA form, when you write it in the form of 1 minus something b, 1 minus something b to the 12, you're always going to have that b to the 13 term that S2 doesn't have. So let's say S2 lacks the b times b to the 12 term. Is not SARMA, at least in the usual way of writing it. Okay, and that sort of may start setting us thinking: is that a big deal? Is S3 really better than S2 because S3 is a SARMA and S2 isn't? And that brings us to question 6.2. What's the purpose behind this multiplicative structure? Is it a theoretical advantage, a practical advantage, or disadvantage? And we should think about that. What should we say? So the multiplicative form is, it is convenient for data analysis. Let's think, why is that the case? It separates the annual and monthly effects, right? It has a nice product form with simple and interpretable roots to the ARMA polynomials. Okay, so that it is convenient in that sense. I don't know of a scientific reason to prefer the SARIMA specification. Let's say let's say there is no scientific reason to prefer S3, which has the SARMA form, to S2. If you do know a scientific reason, I'd be interested to hear about it. Okay, so we're going to try fitting a SARMA model, and now we can fit monthly data, because whenever you have monthly data in situations like well, and anything related to the natural world is very likely to have seasonality on an annual cycle. And so now we can analyze the monthly Lake Huron depth data. The original data come with year and month columns. We're going to put that together into a time variable, which is year plus month divided by 12. Well, you have to decide for this whether January is 1/12 or 0. Here I figured that probably the December data were accumulated to the end of the year. So in some sense, the December data should correspond to the very end of the year. That's how I've done it. Okay, here's the data. Based on our previous analysis, we could fit an AR1 model for the annual polynomial. Last time we were just looking at annual data. We have to do something for the monthly part. Let's just start off by trying ARMA 1-1. And what we're fitting then is this model that's in equation 1 here. So we have the monthly and annual parts multiplied together for the AR1, and just a monthly part for the MA part. And then here you see the R code on how we fit that. To add the seasonality, we add a seasonal component to the ARIMA model, which has both an order and a period. So the period here is 12 because it's monthly, and the order is 100 because we're doing an AR1 for the annual part. And here is the fitted model. We have SAR for the seasonal AR1. Maybe there's not so much to say about this until we could compare it to other alternative models, or we could do residual analysis. Well, here we have a residual analysis. So it's a similar issue to non-seasonal ARMA models. You look for correlations, but in the autocovariance plot, you may be particularly interested in correlations at lags corresponding to multiple of the period if you had misspecified annual dependence. Here, at least what I see some indication of a decaying oscillation going on down here. And let's say the oscillatory component of the residuals suggests an AR2 specification for the residuals. And if we add AR2 to the 101 cross 100, we get 301 cross 10012 for the whole order of the SARMA. And well, when you're doing a residual analysis like this, just looking at it by eye, well, why is it AR2? Because AR2s can oscillate and AR1s can't, but you don't really know if the evidence is strong enough or not. It just gives you something to try. And so let's say this heuristic suggests a model to fit. I won't say, but it's not a substitute for something like AIC or a likelihood ratio test. We then want to quantify our heuristic reasoning. Okay, so now the next thing we're going to look at for extending ARMA modeling is dealing with difference data. Dealing with difference data means you have to integrate back to a difference model to get back to the data. So they're called integrated models, even though they involve differencing. Applying a difference operation to the data can make it look more stationary, therefore more appropriate for ARMA modeling. Remember that we're usually interested in fitting stationary ARMA models. And so if you want to fit stationary models and your data don't look like they are well suited to a stationary model, you transform to stationary. This is a very standard way to transform to stationary. So we have the ZNs, there's the difference of the YNs. An ARMA model for the difference data is called an integrated ARMA model for the original data, and it's written as ARIMA. I is for integration, and we've taken a first difference, so it's ARIMA with a difference term of 1. In general, you can write down an ARIMA PDQ model where you take the dth difference and model that as ARMA. Well, one other thing that I've done in S4, I've also included the mean. So it's the dth difference is a mean mu ARMA. And just as before, epsilon n's white noise process and phi and psi are ARMA polynomials. So you can try different degrees of differencing. It's somewhat unusual to fit an ARIMA model with d greater than 1. So if you do want to fit d greater than 1, the burden is on you to show quite clearly that's a good thing to do. One thing you might notice about the ARIMA P1Q model is it's very close to being an ARMA P+1Q model with a unit root added to the model. And let's just think about why it's almost not exactly the same. Well, there's a little detail that's different, but it can be an important difference to bear in mind in practice. So let's say note the differences in the treatment of mu. So for ARIMA, mu is the mean of the difference process. Now let's think about the consequences of that. Let's look at the case D is 1. Then we have that the expected value of 1 minus b yn is equal to mu, and that means, so the expected value of yn plus 1 is mu plus the expected value of yn, which means if we solve that, the expected value of yn is some constant a plus mu n. So you have the mu in an ARIMA with d is 1 corresponds to a linear trend. Let's write that down, corresponding to and if we just write mu as the mean of the ARMA, then you don't get a linear trend, so that's the difference. Now, when you're doing data analysis, you're starting to think about your projects, you're thinking that maybe you need to transform to stationarity, maybe you should consider differencing. Here are two different reasons to fit d greater than 0 in an ARIMA. So one is sometimes the difference data is just the right thing to model, and the S&P 500 stock market index analysis is a good example of this, because the difference of the log of the data has an interpretation in finance of the return on the stock over that time interval. Sometimes we difference just to make data look more stationary, and essentially that's using it as a way to justify applying the ARMA machinery for fitting a stationary ARMA. You can do that, and sometimes it's a reasonable approach. You have to be cautious about it because it can lead to poor model specifications, hence poor forecasts or other conclusions. Why is that? I think it's, you'll see when you're doing data analysis and you try differencing your time series, it makes it look nice and stationary, but it also throws away a lot of pattern. So for instance, a linear trend just becomes a constant when you difference it. I think differencing really entered the culture of fitting ARMA models. That's partly because ARMA models grew to be very popular quite a long time ago now, in the 70s and 80s. And at that point, you didn't really have any alternatives. Computers weren't powerful. And so you basically needed to use ARMA methods and method of moment estimators that were very computationally favorable. And so if your only practical option is an ARMA model, then you're going to spend a bunch of time trying to shoehorn your data into that analysis. So here's some practical advice on using ARIMA models, which you may want to think about as you do data analysis. So ARIMA analysis is relatively simple to do. If you have a simple time-honored statistical analysis, you should at least try it as one of the things to try in your data. It's been a foundation of time series analysis since the influential book Time Series Analysis of Box and Jenkins back in 1970. And so generally, a practical approach to data analysis of time series is to start with an ARIMA analysis, and either it's successful and that you've quickly solved your time series analysis problem, or else you identify potential limitations, and that will generally require more advanced models and methods. And then just because you've done something more fancy doesn't mean that that worked out better, but you can, once you have two different analyses, you can compare them and see whether you've learned anything new. One more thing we can do, putting all this together, if we put together integration and seasonality, we have the so-called SARIMA model, PDQ cross big P, big D, big Q. There are a lot of different models that can fit into this. You have to choose 6 different orders before you've even estimated the parameters. And fortunately, using the ARMA polynomial method, you can write this model in a general form quite readily. And I've done that in equation S5 here. Epsilon n's white noise process, mu is an intercept that models the trend of the, well, I guess it's the mean of the different y's. And because there's so many models that fit into this framework, people normally only use very small values of PDQ, big P, big D, big Q. And one particularly famous example that seems to be useful in quite a few situations is SARIMA 011 cross 01112 is used for monthly forecasting in economics and business. And it's sometimes called the airline model, after a data analysis by Box and Jenkins that popularized this particular model. Well, we're going to move on in the next part to using ARMA methods for regression and estimating covariance.